guest presentation, and then we'll have a little bit of a break to set up for the countdown round, and then that'll be followed with the awards presentation. So, I'd like to just introduce our speaker. Today we have Professor Haruta from the University of Hartford. She earned her undergraduate degree at Smith College and her graduate degrees at Boston University. She's a professor here at University of Hartford, and today she's going to talk to us about number patterns and problem solving. So please join me in welcoming Professor Haruta.
Thank you very much. We've been playing around a little bit with the technology. So first question is, I can really hear myself. Can you hear me? Yes. Am I making you deaf? No. Okay, good. Because usually in my classroom I do a lot of shouting, so I'm not used to being mic'd. And I also feel like I should be selling the ShamWow right now with this, or maybe Geico Insurance. Anyway, thank you very much for coming to this portion of the MathCounts event, States Competition. I know it's a very exciting day for you. I have actually been here in the past as only an assistant coach. Mr. Smith I had the opportunity of working with and with his students at Henry James, and I've also been here as a parent. I know that it's a very, very exciting morning. There's a lot of excitement about the competition and the pizza, so hopefully you had a good lunch. So what I'm going to talk about today is patterns and problem solving, and I'm going to do a little bit about talking about what it is to be a mathematician, and also what kind of patterns mathematicians like to look for, and what we find interesting, and probably what you find interesting. So first question, I know that this is a middle school presentation, so how many 7th graders do we have in the room? Okay, quite a few, all right. And then how about 8th graders? Okay, and parents, some parents here, good, good, and of course, coaches and assistant coaches, yes. All right, and a big hand of applause for the coaches. They're just fantastic, and the support that the parents give is really, really terrific. So, how many of you like math? Okay, let me hear it. Yeah, okay, good. I figured you wouldn't be here if you didn't like math. But here's a question. Do you ever think of yourself as a mathematician? You probably don't say, yeah, I'm a mathematician if you're in 7th grade. But if you're solving problems and you're looking for patterns, then you really are thinking like a mathematician. And right now is when you're starting to become a mathematician. Now, it doesn't mean that means you're going to be teaching math, which is what I ended up doing. It doesn't mean that you're going to end up solving problems for the rest of your life or being an engineer. But as long as you're thinking about mathematics in an exciting and interesting way, then you really are thinking like a mathematician. And for those of you in the audience who just aren't quite sure what you want to study in the future, I just have to make a confession. I started out as an English major, and in junior year I had the most amazing math course, and I went, I want to be a math major. And I was much better at English, but I was having a lot more fun in math. I thought that I would never teach math, but then I ended up being a teaching assistant when I was at Boston University, and I absolutely loved it. So I spent, a little bit about my background is I spent 4 years teaching at Buckingham Browne and Nichols School, which is a upper level high school, it's their upper school. And then I came to the University of Hartford in 1992, which is giving away my age. I've been here for a long time. I've really enjoyed teaching college. I loved teaching high school, but I've worked in the schools with 2nd graders, 5th graders, 6th graders, gifted groups, so really all ages. At the university, I teach a lot of students who are in engineering, the health sciences, science majors, but I also really enjoy teaching courses for students who are just plain scared of math. So there are oftentimes students who are in the arts, music, and they come in absolutely petrified, but we end up playing a lot of games, and one of the things I tell them is that mathematics can be really beautiful and fun, and you can think of it as a puzzle or an adventure, and so we actually end up doing that in the class. So that's what we're going to do today, so let's get started. We're going to be exploring numbers and patterns, and we're going to be looking first at something called sequences. Now, as I'm talking today, there may be things that you recognize and that you've seen, and there may be some brand new things that you've never seen before. So a couple of rules, and you know these from MathCounts. Raise your hand if I ask a question, and no shouting out, no spoilers. You might just go, oh, I know that, I just read about it, I learned all about it. Well, let the person next to you figure it out, because you're all at different stages. So I will be asking questions. I don't have frisbees to toss into the audience like they may have later, but I will be able to give you a chance to talk. So keep your eyes open, your brain's busy, and let's get started. When you're looking at these questions, there's a few things you always want to think. There's a bunch of numbers, there's a pattern. What could I do next? Like, what kind of games could I play? What sort of patterns are there? And then also, what connections are there between patterns? So the first thing that we're going to look at are sequences. So here's a sequence. So you want to think about, what do you see? What sort of pattern is there? And somebody see a pattern. What do you see? Yes, you. So if you want to get 3, how do you get 3? 1 plus 2. And if you want to get 6, 1 plus 2 plus 3. Anybody else see a different way of thinking about it?
They're triangular numbers, so for any number, for any term n, the number will be n minus 1 plus n.
So you're seeing something that has a special name called triangular numbers and a formula that goes with it. Anybody else see? Yeah, go ahead. No. Okay. A yes, then a no. One more. Yes?
For a certain triangular number, if you
I'm sorry, for a certain...
a triangular number, if you have that many number of dots, you can arrange it in an equilateral triangle.
Okay, so we're starting to really branch out into all kinds of patterns. And the thing about any kind of pattern is there are a lot of ways to look at them. You can see lots of different patterns. So here we have, and can you see kind of well enough? It's a little bit faint. 1, 3 is 1 plus 2, 6 is 1 plus 2 plus 3, etc. to generate this sequence. And we'll actually come back and see these later with the name triangular numbers. Okay, here's another one. So anybody recognize this sequence? Yes, with the green jacket. The primes. Okay. So how do we go from one to the next number?
Each number is the lowest number which is not divisible by any previous numbers.
So you've just given us a very nice definition of what a prime number is. But do you see how I had a pattern at the top? Like it could always get the next one? How do we get the next one? This is a really, really important question that a lot of people are studying today. These are the prime numbers, and so we'll find them occurring in some of the things that we're looking at today, and actually joining some mathematicians in their hunt to try to get some answers. So let's look at another sequence. So I'm looking for, what do you see as far as how do you get the next number? Yes, so tell me what you're seeing. You're adding powers of 2. So to get from 1 to 3, he's added 2. To get from 3 to 7, he's added the power of 2 squared, and then 2 cubed. All right, and how about you? Double the previous number and then add 1. So double 1 and add 1, we get 3. Double 3 and add 1, we get 7, etc. And anybody else? Okay, odds again, yeah? What else? Besides those?
Is one of the powers of 2 minus 1.
So if we take 3, what power would that be? Minus 1.
That would be 2 squared.
2 squared minus 1. And then 7, 2 cubed minus 1. So these patterns are all actually interrelated, but we just had 3 different ways of subscribing how to go from 1 to 3 to 7, etc. All right, so we've got 3 different ways. Did you guys see my slides? I mean, that was exactly the order practically that I put them up in. All right, so let's take a look at another one. Now, remember what I said earlier, no spoilers. So I know that hands up mean that you know something about this. So just think for a second. If you've never seen this before, take a minute. It's really cool. And think about it. Okay. All right, so I have an answer back here. Go ahead. You've got a name for it. Fibonacci sequence.
The numbers are made from adding the 2 say 3 is made from adding 1 and 2 together.
Uh-huh.
1 is made from adding 2 and 3 together. So each number is made from adding the 2 previous numbers together.
So you add the 2 previous numbers to get the next one. 1 plus 1 gives us 2. 1 plus 2 gives us 3. And so on until we get the sequence, which is called, which is called the Fibonacci sequence. And I saw a hand up in the front. Was there any other additional? No? All right, so Fibonacci sequence. All right, so let's start playing around with things. I worked with a group of 5th and 6th graders a few years ago, and they called these cool numbers. So, because numbers are cool. So, I'm going to represent the numbers with dots. Right? So there's the dot. Now, some of you probably know where I'm going with this. Seen that before, yes. Triangular numbers, and there's the triangle that they're named after. So let's do this again, because remember what I said earlier, whenever you're doing something, think, what could I do next? How can I play? You got a triangle, how about moving to a square? Not too complicated. So, what are these called? These are a little bit more common, yes, with striped square numbers, right? Okay, triangles, squares. Let's just keep going. I'm going to come up with another shape. Ooh, who's played with these before? What's that? Shout it out. Rubik's Cube, right. These are actually my son's Rubik's Cubes. I took pictures of them. So, you start counting how many little blocks there are, and you get another shape. And they are a list of cubes, so we'll call these the cube numbers. These are figurate numbers. They're numbers that are based on a shape, and there's a lot of different ones. All right, so we have some patterns. Some of them were familiar to you, some of you figured out as we were looking along. Let's go to some puzzles, because I know you guys are great puzzle solvers and problem solvers. The question that I'm going to put up now, again, no spoilers if you know the answer. I'm going to put up a picture. I'm going to ask you a couple questions about it. You might want some scrap paper. Maybe you're really good with doing this in your head, but here's pattern of numbers, first of all. Let me precede this with a pattern of numbers. Take your triangular numbers, and remember that, and you may actually be able to do this in your head. Triangular numbers, 1, 3, 6, 10, 15. Now, when you were generating the sequence, you looked at differences. So, should we do it again? What happens? So So when we took the differences, we got 2, 3, 4, 5, because that's the triangular numbers. You add 2, then you add 3, you add 5. But if we do another difference, it's always 1. So if we want to figure out what the next triangular number is, we can reverse the pattern and do something called finite differences. So if you're looking for things to play around with and learn about, finite differences is a whole topic in and of itself. Leads to some interesting things in algebra. We're going to look at the difference as 1. That gives us the 6, and backwards we go to 21 in the sequence. Let's take a look at how the cube numbers work. So there's our cubes, 1, 8, 27, 64, 125. So picture the differences. Differences again, maybe. One more time. Hey, now we're back at constant differences. Took a little bit longer. So if I were using fourth powers, a good question would be, how long would it take me to get to those constant differences? Is there a pattern going along? And I'm going to back up slowly to generate the last one in this particular list. Now I'm seeing hands go up. Are these questions or? Yes.